section. Welcome back, everyone, to this afternoon session on the epoch of reionization and galaxy formation. And the first speaker will be Joe Lewis from the University of Heidelberg, talking about cosmic dawn 3 and the latest constraints on the mean free path of ionizing photon. Take it away.
Thanks, Amandine. So I'm Joe. I'm currently at Heidelberg, kind of working for the enemy, I guess, of Ramses, because I'm working with Illustrious TNG and the repo. But today, I want to talk about Cosmic Dawn 3, which you heard about before the lunch break. And I guess our first exciting science results. So that concern the mean free path of ionizing photons. I have the usual boring reionization slides. They're particularly boring because Pierre already showed some. But by now, everyone knows that reionization is a universe-wide transformation of the IgM hydrogen that was gradually ionized by the first ionizing sources in galaxies. And because of its source-driven nature, it gives us a window into galaxy formation at early times. So because of the extreme distance that separates us from this epoch, and the fact that there's so much neutral hydrogen between us and the ionizing sources means that direct observational constraints are really challenging. They're often very indirect. And today I'm going to talk about the mean free path. So what the mean free path is quite explicit once you've heard the name. And so it's just the average distance that the ionizing photons can expect to travel before encountering an unhappy, unionized hydrogen atom in the IgM somewhere. So this is an important number for people like us who are interested in reionization, in particular because it's obviously linked to the ionization state of the IgM. But actually, it's also quite useful because it's linked to other common reionization properties like the photoionization rate. Okay, so until very recently this year, our picture from the observational point of view was something like this on the right, which is a plot I stole from a George Becker paper. So you can see that all our previous observations sat somewhere on this nice power law. It's very nice of nature every time things work in terms of power laws of redshift. But actually this year we learned that that was not true at all. So this new point from the George Becker paper at the redshift of 6 is the highest redshift determination of the mean free path we've ever had. And you can see it's in clear conflict with this rather ambitious extrapolation here, which makes sense because reionization is still ongoing at this time, or at least ending. And you expect there to be some large changes in the average ionization of the IgM and thus of the mean free path. So what's interesting for you guys, I think, in this is that actually from a theoretical point of view, these new observations are quite tricky to explain. So this is another plot from the same paper, which shows at the time existing simulations and models attempts to predict the value of the mean free path. And you can see that whilst the existing lower redshift points are relatively apparently easy to match, this higher redshift low mean free path remained quite far out of reach from previous work, okay? There have been a number of papers this year trying to address this, and one of the most recent ones and the most successful was this paper, this result from Kane. So on the right, you can see their attempts in the red full line and the black dotted line. So you can see that already they're much closer to reproducing this low mean free path of the redshift of 6. However, they're, I guess, maybe it's not the proper way to say this, but they're kind of in a marginal agreement. And at the same time, their agreement with the lower redshift data points, is even more marginal in a way. Where can we go from this point? Well, it turns out that all of the theoretical works that I've showed you so far have attempted to address this problem using simulations where radiative transfer was not fully coupled to the hydrodynamics and star formation of the cosmological simulation. So let's try and do that in a fully coupled simulation. So let's make a very basic wish list. We need it to be big enough to actually measure the typical mean-free path. We want fully coupled radiative hydrodynamics, as I've just said, and we also want a good match to IgM ionization constraints because we want there to be a realistic reionization happening in the simulation box. So I've kind of spoiled you with the title, but we're going to use Coda 3 to do this. And just to go back over the bullet points, is it big enough? Yes. Does it have fully coupled HT? Also. And I want to focus on this last point, which is let's say the agreement with the constraints we have on the ionization of the IgM towards the end of reionization. So a lot of you in the audience are aware of these kinds of problems, but typically in these fully coupled radiative hydrodynamic simulations of reionization, you tend to overshoot the ionization at the end of reionization. So you end up with things that are like this on the right, which is our result from Cosmic Gluon 2 in the black thick line, where you can see that the average neutral fraction is much lower than was expected at the time. So we don't really have the time to get into this, but we'll probably could go over these data points as well, the constraints used. But it remains that these simulations tend to have an excessive number of ionizations, and their end of reionization neutral fractions are too low. So we've been looking for a way out of this, and as Pierre already mentioned, we have found one. Okay, and so for this we turn to a result by Kulkarni et al. From a 2019 paper. And to calibrate their simulations, I actually turned directly to the observations of the optical depth in the Lyman alpha forest, as opposed to constraints on the average neutral fraction, which requires some kind of modeling. So for us, this implied some tweaks to our star formation model and higher resolution. These are the main two changes, I suppose. With this new calibration, we obtained something similar to what's happening on the right here in this plot, which Pierre already showed you. So this is actually from a calibration simulation for Coda 3. And so the important takeaway is, again, as Pierre explained, that the ionizing emissivity, so the number of photons we produce that actually make it to the IgM per second and per unit of volume, rises throughout most of reionization, but towards the end falls off and actually decreases. And this is brought about systematically in our simulation, as opposed to the Kulkarni work where it was tuned like this. And in our case, this arises because of low escape fractions in high mass galaxies. And at the same time, star formation suppression in the low mass galaxies that drive reionization. So this is a very fundamental change in the picture we had, which before the ionizing emissivity used to increase constantly. And so you can guess from this that this is going to help with our excessive ionization problem. So let's get to that right now, shall we? So here I'm showing the average neutral fraction as a function of redshift again, in both Coda 3 in the blue full line and Coda 2 in the yellow-orange color full line as well. And so you can see that the two curves are quite strikingly different, with Coda 3's reionization ending later than Coda 2, so we have a late reionization. But moreover, this kind of foot here of the average neutral fraction curve is in very close agreement with the latest and updated constraints on the average neutral fraction, which is a dramatic improvement to where we were with the first simulation. So not only have we changed our picture, but it seems that observers have as well. So another way we can look at this is through the average ionized gas ionization rate, okay, gamma for short. And so this is linked obviously to the ionization state and the source population in the simulation. And so you see again with the same color codes that the CODA2 curve was excessively high, which makes sense. We had too many ionizations, so too high average ionization rate, and correspondingly a neutral fraction that was too low. In CODA3, you see the situation is much better and actually go quite nicely through this combination of constraints here on the right. And so as a matter of fact, the average ionization rate can be linked through some assumptions and modeling to the mean free path, which we're going to get back to straight away. So here I'm showing on the right the mean free path as a function of redshift in CODA3. That's the blue line with the error bars. And again, you can see the newest Becker points here in orange, yellow, and the older Vorsac ones in this kind of brown off color. And you can see that CODA3 is an excellent match to these observational data. And that's in particularly due to the strong evolution of the mean free path that happens between a redshift of 6 and a redshift of something like 5.3, 5.2. So this strong evolution places us far, and the agreement with this observational point here at redshift 6 puts us far below the mean free path predicted by other theoretical work, which probably has some strong implications for the state of reionization in their simulations at these times. So what does this imply? Well, this seems to say that there is something missing from these other theoretical works where radiative transfer is not coupled to the hydrodynamics in star formation. The other things that are important for us is that this confirms that late reionization in our simulations is definitely a good thing when we're trying to reproduce these latest constraints on the ionization state of the IGM. And at the same time, that this revised star formation model leading to the state of suppression we have in the low mass halos that drive reionization is crucial for the lower redshift end of reionization ionization values. So that's more or less what I've planned for today. So I can leave you with an outline of where this leads us. And so obviously we're going to go back into the simulation and look at the constraints on ionization in more detail, and also turn to more in-depth analysis related to galaxies such as luminosity functions, for which we now can actually produce some kind of coherent, consistent extinction based on dust densities that we have thanks to lots of help from Johan. And then I'll be, of course, renewing my work that I did in CODA2 on the escape fractions of ionizing photons from galaxies and the ionizing photon project. And at least in my case, this will keep me busy for some time. So I think that's enough to talk about. Thank you for your time. I went a bit quickly, so please go ahead with the questions. If there are any questions.
Oops, I wanted to clap, not raise my hand. So. Any questions? And thanks, Joe, for allowing us to get back onto time. Yes, Ali.
So first, a really nice talk. I have a couple questions. So can you talk more about the stall formation routine and then how sensitive the results are to that? And then the second question I had was when we calculate the mean free paths in Sphinx, we find that instead of having one peak, there's almost two peaks in the mean free path. There's the long one, which is in the sort of IGM, and then there's the shorter ones, which is a bunch of photons escaping galaxies hitting a sink immediately. So I was wondering if you guys see something similar in CODA, and then whether or not the mean in terms of mean free path is actually a good summary statistic of what we're looking at.
Okay, there's a bunch of interesting questions, thanks. So regarding the star formation model, the main change we made was to require to implement a temperature threshold for the star formation to happen. So there's the way it works is there was a density threshold, and now there's also a temperature threshold. So we're assuming that the gas that forms stars cannot be hotter than the typical photoionization temperature. And we're assuming that in all of our cells. Okay, so we're assuming that there isn't unresolved overdensities that could cool and form stars in our cells, which is probably debatable, but it's something that a lot of people do and have done. And for us, this has got us to an exciting new place. So we're quite happy about it in terms at least of how reionization happens in our box. And we still match what we need to in terms of the luminosity function and the density of star formation. I hope that helps answering your first question. Regarding the second question, I'm not entirely sure what you mean by the peak of the mean free path.
So what I mean by that is if you actually plot, I don't know how you guys calculated the mean free paths, but if I just shoot a bunch of rays through the box and I plot up what the distribution is, you'll find that it's actually in a lot of cases bimodal, and then from high redshift to low redshift, the stronger of the peak moves much closer towards the longer mean free path. So then when you actually take the mean of that value, especially at these like intermediate redshifts when percolation is going on, you'll find that the mean is actually in between the two peaks. So it's not actually representative of either. So I was wondering if you see anything similar.
So I agree with you that representing this complex distribution of ionized bubbles with one number is always a tricky thing and probably a wrong thing to do. From our point of view, we're contenting ourselves with reproducing what, at least to the best of our knowledge, what observers are throwing at us. And we're going to study the exact distribution of transmissions and stuff like that in more detail in the coming months. Yeah, we have looked at this, and they're definitely the similar shape in the distribution of line of sight transmissions.
Martin?
You showed this plot of...
Briefly.
What?
Briefly, because I hope your question is brief.
What?
Don't worry.
You showed this plot FH1 of the neutral fraction and sort of said that the observers have changed their plot as well. I think the real observation is actually the effective optical depths. What the observers plot there is already using the simulations to turn this into an FH1, or in case of Fan et al., using an analytical model to turn it into an FH1. So I don't think the observations have actually changed that much as this plot implies. This is actually a model interpretation of the data. The real thing is the plot you showed before, the tau effective, and the distribution of the tau, which has become better too, but I don't think it has changed by that much. This was the only comment I had. And for the tau effective, you're still sort of hugging the lower end of the observations.
No, I agree. Yep, this was, I'm sorry if it surprised you. I guess it was a shortcut to go quickly in the talk. But yeah, the real things we want to look at are the effective optical depths.
Then let's thank Joe again, and Sean, Barrett, could you please set up?
Yeah, does that look okay?
Yes. So now we have Sean Barrett of the University of Oxford talking about radiation-coupled primordial chemistry in simulation of the first galaxies. Go ahead.
Great, thank you. Yeah, so I've implemented a model of primordial chemistry coupled to the radiation Ramses RT. So I'm going to quickly explain why I'd want to do that and what that means, and discuss how I've implemented that, how I've tried to verify that the physics is correct, and quickly at the end I'll tell you what I'm looking forward to doing with that code in the near future. So why should you care about chemistry in the early universe? So there are no metals around to cool your gas. The only way to cool enough to form stars before there are any stars is to form H2 and its deuterated counterpart HD. It turns out, despite there being no metals around, there's still quite a lot of chemistry that can happen. I've just written down a few reactions on the right that show the main formation process of these coolants, but obviously there are many more reactions to consider in the whole system. And because we're thinking about simulating galaxies, we need to go beyond the point of the formation of first stars and consider the effect of radiation on cooling primordial gas. And it's important to note that this is not an equilibrium problem. This is the timescales over which the chemistry changes and the gas cools are similar enough that you, in a simulation, to get the best accuracy, you need to simulate these at the same time. So you need to do your hydrodynamics and solve your chemical system. So quickly, what Ramses RT does, at least the public version, it does not treat H2 in a non-equilibrium way. Its cooling function assumes an equilibrium concentration of H2 just as a function of temperature and density. That's not a criticism of Ramses RT. It's just there are reasons why you wouldn't want to do it the way I do it also. And it's also worth mentioning that the semi-implicit scheme Ramses RT uses by default works great for Ramses RT, but makes it difficult to extend the thermochemistry with a very large system of ODEs, because the semi-implicit scheme doesn't capture very well coupling between variables. It needs you to do at least 2 time steps to get kind of a bidirectional coupling, which we have a lot of in chemical networks, so we needed to take a different approach. So on the right is the actual system of equations I use, minus a few deuterium ones. And I use some software called Chrome, which takes this list of equations and associated reaction rates and outputs some Fortran code to solve the system of ODEs associated with the equations. It does this with an implicit adaptive solver. And it's important that it's implicit because that means it can capture coupling between equations in a single time step. So while it is more expensive, to get the accuracy you want, it will end up being more efficient than the Ramses RT scheme. It turns out to be very slow because it's a very big system and quite a sophisticated solver. There's a big matrix to solve and invert. And also note that I include all the photo absorption reactions in my chemical systems. This is the way it's coupled to radiation, because the photo absorption and the rest of the chemistry are tightly, numerically, tightly coupled equations. They each affect each other very much. We need to solve them at the same time, otherwise our accuracy struggles. So the way I've tested the code is to look at two main situations where I think the chemistry will have the largest effect, which is in photoionization dissociation and in gas collapse by radiative cooling. So the way I've tested the ionization is to look at a suite of Strongren sphere-like simulations. So that would be a star in a corner of some homogeneous gas. And there's one I picked out to look at today, which is particularly interesting because it demonstrates a numerical point. So this is a star in a box of homogeneous molecular hydrogen, so not a normal Strongren sphere, but and I've done 2 simulations here, one with a decoupled temperature update, and by that I mean in my time step I solve all my chemistry and photo absorption, and then explicitly update the temperature the way Ramses would do it. And on the right, I've included the temperature ODEs in the whole Chrome systems that are all being solved at the same time. So on the left, you can see the H2 fraction and the H fraction are, we have a very sharp ionization front and a kind of H2 formation artifact at the back of the front. And more importantly, we've very much overestimated our dissociation rate and ionization rate. And indeed, the temperatures are higher here too. So when we're doing simulations of reionization, it's very important that we don't do this. So this is just demonstrating that we've had to essentially rewrite our RT cooling module to roll every ODE into this big system, because separating them out just negates the whole point of doing using a more sophisticated solver. And I've also been interested in testing idealized cloud collapses. So this is something star formation researchers study very well. I use as a model to test my code. So I found this paper by Omika and others from 2005, where they use a chemical network very much like mine, and indeed mine is based off of theirs, in a single cell model where they force the density of the gas to go as a power law, an idealized power law. So they don't do hydrodynamics or gravity, they just do a zero-dimensional model. And what I'd like to be able to do is reproduce this temperature versus density curve with a 3D simulation. So that's what I tried. This dash curve is a 0D model in the same style as Omika, but using my slightly modified chemical network. And this blue curve is with a 3D hydrodynamic simulation. So they're very similar at the start when the adiabatic collapse. Then gas gets very dense, starts to cool. And we're pleased to see this turn over at a similar temperature, but there are still discrepancies. So this flattening of the profile is, I believe, a resolution effect. So at the higher densities, we don't necessarily refine enough. So we underestimate the density and underestimate cooling rate. So our cloud doesn't continue the collapse as it should, but we do see as we increase the refinement, this moves down a bit. So I'm kind of reassured that this is a natural result of the hydrodynamics and not an error in my network. So anyway, what I plan to do with the code is to resimulate a collection of dwarf galaxies that were first published by Tayson Kim and Harley Katz and others. I think all the authors are in the room, in fact. But adding on my chemistry and revamped cooling module to see what effect this has on actual simulated galaxies rather than in theory. I would have liked to show you one of my own simulations today, but we've been having some supercomputer trouble. But if anyone's interested, I might be able to post a picture to the Slack in the next week or so. So it's very exciting at the moment. We're getting very close to science runs with this. And yeah, I'll answer any questions now. Right.
Maxime? Maxime, you're muted. Maxime, we still can't hear you.
The microphone is playing again. Is it better now?
Yes.
Okay. So thanks a lot for the talk. I really enjoyed to see the coupling with Chrome starting to like get in shape. I'm sure it's really expensive. Just like going back to your science goals and the things you want to do next.
Yeah.
I guess if you start to have molecular hydrogen like properly done in radiation, one goal will be to look at population 3 stars, right?
Yeah.
Do you have any idea where you like how you would do that in terms of modeling the star particles and what kind of IMF you would want to use or that kind of thing?
I haven't thought about that too much at the moment. So I'm looking more at the full galaxy simulation, but it could be, it's definitely one kind of appropriate application of the code. But yeah, no, I haven't looked into doing particularly simulations of the formation of individual stars yet. No.
That looks extremely cool, though.
Thank you. Sam or Ilian?
Ilian's first.
Okay.
I have a couple of questions, maybe a bit technical, but have you thought, I mean, there is no too much point of doing H2 chemistry without doing the Lyman-Warner radiation transfer, because you have all the wrong abundances. And the other question is, does your chemical reaction network differ from what has been done before? I mean, these things have been done since the late 80s, right? So there is plenty of literature before. Is this actually different, or you are solving pretty much the same equation, just different method?
Oh, sorry. I'll stop sharing my screen. But I think the network itself is more or less lifted out of the Omakai paper, but it's not fresh by any means. But the difference is that I do the Lyman-Werner radiative transfer. Everything is coupled to the radiation of Ramses RT. So I think this combination of the radiation and the chemistry is more new, as far as I can tell. If that answers your question.
And how is the Lyman-Warner radiative transfer done?
Yeah, so I haven't talked about the self-shielding processes, but yeah, so I use a table from the Leiden database on the H2 for the H2 absorption cross section. I integrate it over our stellar SEDs to work out the average cross section over the Lyman-Werner bin, and I use the self-shielding prescription of Sarah Nickerson, who published a paper in 2018 about non-equilibrium H2 formation in Ramses RT.
Okay, thank you.
If that's what you mean.
Go ahead.
Hey, yeah, nice talk. So I guess I have a couple of questions. So the first one is this appropriate for low but non-zero metallicity chemistry, or would you need a more expanded network to do that? And the reason I ask is that there are a lot of low surface brightness galaxies where you also have star formation, where it's interesting to study feedback.
So I guess it depends how pedantic you are about your metal cooling. So it's easy to add in kind of the standard Ramses scheme for metals and metal cooling. And Chrome has its own opinions on how this should be done as well. You could track the individual metals, but obviously with every equation you add comes a large performance cost. Right. But yeah, and in theory, this is quite easy to extend. It's just a matter of how much computing time you can throw at it.
For sure. Okay, but yeah, that could be interesting. I mean, another problem is, so I've been involved in a project with a repo, which I think is still not published because the person the first author left science. So I think it's been kind of shepherded over the line by other people. But they're also looking at zooms and H2 regions around population 3 stars with the idea of, can you shut off accretion? And I think, when you zoom, you get a lot of interesting effects because obviously the effective density changes. So yeah, definitely be interesting to see this kind of followed up on, because I mean, one of the problems is also the ray tracing in a repo can be very expensive. So if you have M1, I think that saves you a lot of time.
Yeah. I do expect to have some simulations out soon.
Awesome.
If not for some technical issues over the weekend, I might have been able to show one today.
Okay.
Hi, Sean.
Hi.
Very cool. I agree with Maxime and the others. Super cool. Maybe a bit complicated question. So when I was doing the RT cooling module way back, I found this problem where I had to do a lot of subcycling for the cooling, because of this kind of inequilibrium between the photo absorption. Well, basically, you had to do a lot of steps because you were always depleting the photons and changing the ionization fraction, and it was always kind of just repeating. You were going back to neutral and then back and forth like that. And I described this what I called smoothing, for lack of a better name, in my paper, which actually speeds up the calculation a lot. So are you familiar with this? Have you seen that? And if so, is it a possibility to do something similar in Chrome?
So I've read about the smoothing. I can't remember exactly how it works, but
so you give a rate of a photon injection rather than the number of photons in the cell. And that allows you to reach easier an equilibrium between the photoionization rate and the recombination rate.
I'm not sure. I would need to have a look. Certainly, if I continue doing simulations of this, it might be important to stop spending so much computing time.
I would be very happy to discuss that later on.
Okay, that'd be interesting. Yeah.
Maybe if there is time for another question. Amandine, is that okay?
Yes, we have 2 minutes left.
Also, is there a flexibility in Chrome to remove reactions that maybe are not super important for the thermochemistry and might speed up the code?
Absolutely. Yeah, so it will solve the reactions you ask it to. So it's all kind of the code is generated for you, and it's very easy to interact with otherwise. So yeah, that's another thing that kind of once I have a big simulation running, I can start to investigate what is actually important about the chemistry. Do I need this huge network or not?
Excellent.
Okay, thanks everyone.
Unless anyone else has any questions, we can move on to the next speaker with Luke Conaboy from the University of Sussex, talking about baryon drift effects at high redshift. Your slide just disappeared, Luke.
Yeah, I just forgot to unmute myself. Okay, thanks, Amandine. Okay, so hello everyone, and thanks for the organisers for offering me a talk. It's been interesting to hear all the fun things people are doing with Ramses. I want to talk to you today about work I've been doing for most of my PhD, which is looking at the effect of relative baryon dark matter streaming velocities and trying to incorporate this effect into cosmological zoom simulations. So this is work I've been doing here at Sussex with Ilian Iliev, and as well as Anastasia, Kerry, and David. So first of all, I'm going to go and give you a bit of motivation as to why this is interesting and why we should try and incorporate this in the first place. Then I want to outline our method with some examples and going through how it works. And then I'll show some results comparing our method with how things are usually done in the literature, and then leave you with a summary. Okay, so to give some context, this is an effect that originates around recombination. So prior to recombination, obviously the baryons and the photons are tightly coupled in a plasma, and the sound speed of the baryon fluid it's relativistic. It's about c/√3. After recombination, or more accurately after decoupling, when the universe becomes transparent, the sound speed of the baryons drops to that of just a monatomic fluid, so it's no longer relativistic. It's about 6 kilometers per second. During this time, the perturbations of the dark matter velocity field have just been growing. So obviously, dark matter doesn't interact with light; it's dark, so it's not affected by the radiation. So it doesn't get the same precipitous drop off that the baryons have. And what you end up with is a relative velocity between the two fluids. So it's of order about 30 kilometers per second. That's a root mean square value. So compared to the baryonic sound speed, which is 6 kilometers per second, it's supersonic. Right? And now the effect that this in places supersonic flow has on the amplitude of baryon perturbations is not typically accounted for through, like, it's formally a second order effect, so it's not accounted for in typical linear treatments, so through the dark ages up to the typical start time of simulations. So Sulejkovic and Hirata were the first to look at this effect back in 2010. They did a simple sort of pressure approach, comparing what happens if you include the effect versus what happens if you just use the standard first order CDM model. So the thick solid line here is just the usual model, and the dashed line here is if you incorporate this relative velocity effect. And you can see from about K of 40 inverse megaparsecs, you get the suppression in the total matter power spectrum. And this is at redshift 40. This effect goes on all through the dark ages and up to about redshift 10 or 9. This is another plot from the same paper. It's just showing the variance of the perturbations in the relative velocity field. And I just want to show this because it'll be useful later on. You can see from about K of 0.5 onwards, the variance drops down to 0. And this kind of tells us that the beyond these scales, the VBC is not really changing. So this tells us like the VBC is sort of roughly coherent over scales of about a few megaparsec, and that'll be useful for later on, but I thought I'd show it here. Okay, so we're by no means the first people to look at this in terms of actually doing hydrodynamic or cosmological simulations. This is a figure from O'Leary and McQuinn in 2012. Each of these panels is showing a different value of the relative velocity. So in the left-hand panel, there's no relative velocity. In the middle panel, there's relative velocity roughly twice the sound speed. In the right-hand panel, it's roughly 4 times the sound speed. And the key, they add in the relative velocity as a wind going in the x direction from sort of left to right, which is typically done. And the key point is that sort of these filamentary structures here get smoothed out, and the higher density peaks also get sort of smoothed over too. And this is because by including this relative velocity, you're reducing the ability of baryons to collapse onto the potential well of the dark matter halo. So baryons are sort of advecting out of the potential well created by the halo, which is why you get the smoothing of the gas distribution. So as I say, this has been done before. Typically, it's small box hydrodynamic or cosmological simulations. So its box is usually less than a megaparsec on the side, and the VBC is included as usually a wind going in for instance, the positive x direction going across the box. So there's some sort of choice there you can pick. People set the baryon velocity to be the same as the dark matter velocity, but just with the magnitude of the relative velocity added in one direction. What we wanted to do is actually source the relative velocity from a larger box. So take a large box simulations, like 100 megaparsec on the side, use that to calculate the relative velocity field. So having the large box gives you a lot of samples, and you're also approaching the BAO scale, which is important for these because the relative velocity is correlated on those kind of scales. Remember, it originates from a round recombination, so it has that connection with the BAO scale. And then you take a patch of this larger box and you resimulate it at very high resolution using the Zoom simulations. So this is what we aim to do. The first step is you generate your Zoom initial conditions with music. So I'm sure lots of you have used music before, but those of you who haven't, it allows you to generate a set of sort of nested grids, kind of like Russian dolls, where you have very high resolution in the center. So this is a slice of the initial conditions of the baryon over density field, and you can see you've got very high resolution in the center, sort of lots of small scale fluctuations, and then as you go out from the center of the box, the resolution slowly degrades until you get to that of the coarser grid. So when we generate these initial conditions, if you use transfer functions calculated by CAM will give you not only separate amplitudes for the baryon and dark matter density fields, but it also give you separate amplitudes for the baryon and dark matter velocity fields. So generating initial conditions in this case naturally gives rise to the VBC field, and you just take the difference of the two fields, and that gives you your relative velocity field. There's a little subtlety here in that one of these quantities is a grid velocity, the other one's a particle velocity. So we interpolate the particles back onto the AMR grid, and then we can just take the difference of the two fields. So now we have the actual relative velocity. We use the fact that over scales of a few megaparsec, it should be coherent, and we split the initial condition fields into patches, sort of about a half megaparsec on the side. And in each of these patches, this is where we incorporate the effect of the relative velocity from recombination to the start time of the simulation. So yeah, this is just showing you split up into patches. And the way we incorporate this effect is we look at each patch and we say, by how much should the density, the overdensity in this patch be reduced if we properly accounted for the VBC effect from recombination to the start time of simulation. So remember, these transfer functions that you get from CAM are just are the linear transfer functions. So you don't include this relative velocity effect. You don't include the effect that the relative velocity has on the density perturbations. So it's like saying in each patch, it's like saying the VBC is 0. So we just take the ratio of what we'd expect the fluctuations in the patch to be given this VBC with what they actually are. And this gives us a bias factor, which looks something like this so the greens for the dark matter and the purples for the baryons. And this is for an average value of the VBC at recombination. So you can see for the dark matter, it doesn't really change all that much, sort of at the 5% level at some of the higher scales. But for the baryons, from about K of 40, the suppression is really quite significant. And this is the suppression that we fold in to the initial conditions. So once we have this bias factor, we just fold it in with each patch. And then you're left with something like this. So this is in the highest resolution initial conditions. On the left, you have just the baryon over density field you get out of music, and the right is after you've folded in this bias factor. So it's essentially acting like a sort of low pass filter, taking out lots of your high frequency modes dependent on the value of the VBC, right? So you could have a region that doesn't have very much VBC in, you wouldn't get much filtering, if any. But if you have a region with very high VBC, you might get a lot of filtering of your high modes. And you can see that here. You can see the small scale noise has been washed out. So that's the way we do it. This is just showing the same thing numerically. So this is just the power spectrum of the baryon over density. So the short dash blue line is the initial conditions you get out of music. So it follows the input power spectrum quite closely. And the red dash line is after it's been biased. So you get the suppression past K of about 40. So to compare with what's been done before, so remember these are typically small box with a constant VBC in them. We do a small box and we apply constant VBC. So this is not sourcing the VBC from the large scale conditions. This is just trying to recreate what people do usually. So we add it in the X direction. And in this test case, I put in just a 2 sigma value, which is about 60 kilometers per second at recombination. I do 3 sets. There's 3 sets. So do one that's like a control simulations where the baryons and dark matter have the same velocity field. One where you have distinct velocity fields, but you don't incorporate this bias factor. So it's like having the VBC, switching on the VBC at the start time of the simulation. And where you switch on it at the start time of the simulation and also incorporate the effect throughout the dark ages. This is the plot of the gas fraction. So this is at redshift 20. So you see that in the control case, you have quite a nice trend increasing towards the cosmic mean. But for the biased and unbiased cases, they're both very, very suppressed. And this is in qualitative agreement with what you get, with what people observed in the literature. So, for instance, if you look at Now's paper in 2013, you see this similar effect. Going forward now, this is redshift 15. The biased and unbiased cases are starting to catch up, but are still quite suppressed. These are for halos that have matched between all the simulations. So match between the controlled, biased, and unbiased by comparing the particle IDs of halos. And this is at redshift 10. So the unbiased and biased cases still starting to look a bit more normal, but still a little way behind the control case. And you kind of expect this effect to be gone by sort of redshift 10 or redshift 9, maybe. This is quite a high value of the VBC that I put in here, hence why they're still
2 minutes.
Thank you. Still showing some signs of the suppression. So this is just laboring the point a bit more. This is the maximum baryon fraction for the matched halos. And you can see you have this suppression below about redshift 20, 25, 26, and 21, where the biased and unbiased cases haven't accreted much or any gas at all compared to the control case. And then the biased and unbiased cases start to catch up quite quickly. Interestingly, there doesn't seem to be much difference between whether you incorporate the bias factor or whether you don't, whether you just turn on the VBC at the start time of the simulation. I haven't looked too much into why this is, but yeah, that's stuff to look at next time. So the next step is running the big zoom simulations, sourcing the VBC properly from the initial conditions. But these are still running and still being analysed. So I was hoping I'd be able to show you some results from this talk, but I'm afraid you have to wait to hear more about that stuff. And that's it. So I'll just leave you with my summary, and thanks very much for listening.
Any questions for Luc? Corentin? Corentin, you're muted.
Yep. Yeah, thank you very much for your presentation. I just have one question, which is once you start including baryons, and if the baryons have like a velocity with respect to the grids, you're also going to get some nasty diffusion effect just because because the grid is not Eulerian invariance. So how can you disentangle that from the diffusion effect, which would be due to the fact that there is a drift between baryons and dark matter?
Yeah, this is true. So yeah, I read this is in your paper, the Edge paper. I haven't thought too much about that yet. This came out while we were still developing the methodology. I mean, yeah, it's quite a complicated question that I'm not sure how to answer. I haven't looked into it too deeply yet. So if I understand it rightly, with the Edge, the work you've done on grid diffusion, you modify the overdensity so that you have, for instance, on the halo you're looking at, you don't have any relative velocity between the grid and the baryons. Is that right?
Yeah. Essentially, you add a dipole, and it cancels the velocity that you have with respect to the grids.
And do you modify just the baryon velocity, or also the dark matter velocity?
Oh, we use the same initial density field for both.
Okay.
There's no question.
Okay. Yeah, the answer is I don't know. It's certainly something to look at, but I haven't really thought about it too much yet. But yes, you're right. Certainly something to be careful of.
Go ahead, Harry.
Oh, sorry. Out of curiosity, Quarantine, we were just talking about this actually like a couple of days ago. Would it be better then to just kick the particles rather than the gas cells to get the? So if you're just using a constant, I obviously understand this won't work in the context of doing a full box simulation, but if you're just doing a zoom in on one halo and you're applying a constant wind, which was, for example, I think Athena Stacy did this years ago, then if you just kick the particles instead of the gas cells, would that give you the same effect? And limit the diffusion?
I mean, in principle, yeah, you'd have to transform to just an isolated simulation, I imagine, because if you're sourcing the relative velocity from the large box, you'd have to transform all the dark matter particles. But if you cut out a patch, then I think you could do that. I don't see why not.
Any other questions? We still have a couple of minutes. If not, let's move to the final talk of this session by Jeremy Fensch. Jeremy, could you please share your screen?
Okay, it is. Can you hear me well?
Yes, we can.
Perfect. All right. So, hi everyone. Thank you for listening to this talk. So I'm going to present you a few projects on the topic of star formation in cosmic noon galaxies. And my main collaborators are Frédéric Bourneau, Florent Renaud, who's here, and Pierre-Alain Duc, and some people in the room. So just to summarize galaxy in a very simplified nutshell, what we think about star formation, galaxy formation, is that here you have a small plot from a review by Natasha Forster-Schreiber and Butte of Milky Way mass galaxy growth history. The star formation rate increases and reaches a peak during what we call the cosmic noon, and then decreases. You create your stellar mass by removing some gas fraction. It looks very straightforward, but it's actually very difficult to properly understand and model. For instance, in the state-of-the-art cosmological simulation, and here I'm talking about, for instance, Illustris TNG, the galaxies at redshift 2, so the cosmic noon, have very strange morphologies compared to what we observed. I mean, the star-forming galaxies are very smooth. They have nice spiral arms. Sometimes they have a bar. Whereas what we see from the Hubble deep surveys is that star-forming galaxies at redshift are mostly clumpy. And also, if you look at their gas content, so that's a plot on the right, which is using and post-processing the TNG simulations, we see that we are missing the galaxies with a lot of gas. And actually, this plot should be seen as something that is shifted to the left. It's not that we are missing galaxies, but that the galaxies are not enough gas-rich. And it's not only a problem of cosmological simulations, and here I'm citing TNG, but also Nihao and Fire have the same problems, but it's also something that is encountered in bathtub analytical models. For instance, this one by Avishai Dekel and Mendelker. It's a very complicated plot, but what the main takeaway of this plot is here the gray zone is the cosmic noon. You can get a right gas fraction, which is half of your bionic mass. But if you do that, your star formation rate is underestimated by at least a factor of 3 between the observations here, the dots, and the lines, which is the model. So it's basically summarizing all the bathtub problem issues that are still not solved. And the main big questions is, how do you regulate star formation in galaxies without ejecting all your gas? This is a question that I will not answer during this talk, because I think it's a goal of a whole career. But I will try to present you some projects that are trying to tackle this issue. So what are we missing in those galaxies? Well, first, redshift 2 galaxies have a very high turbulence. For instance, here you have a very representative object, which is called the Skywalker galaxy. And we see that the velocity dispersion in the disk is around 40 to 80 kilometers per second, which is much higher than what we have in the low redshift universe. And this may have a huge role in regulating star formation for high surface densities. So you can, reminds probably you of the talk by Noé Brussy from yesterday. You can also see it's a very nice paper. And this fact that you have high turbulence in those galaxies may trigger very unexpected behaviors. And one example on which I worked before, it's a kind of an old work now, but it's still interesting to see, is mergers. So if you look at what happens in a low redshift merger, so it's, for instance, the antennae galaxies, part of the gravitational energy is liberated into turbulent motions. And this is this increase of turbulence mostly here in a compressive mode that is creating a starburst and increases a lot by a factor 30 here in the simulation by Florent Renaud, the star formation rate. And this is supposed to change when you have a lot of turbulence, because the amount of gravitational energy you bring will only increase by a little bit the turbulence you have. So here on this plot, you see the difference between two simulations of galaxy mergers for gas poor to gas rich galaxies. Gas poor meaning 10% of gas and gas rich 50% of gas. The gas rich galaxies have a higher velocity dispersion, around 40 kilometers per second before the first encounter between the two galaxies, here at 0. And you cannot increase a lot the dispersion. Here you go from 30, 40 to 50. The gas poor simulation, you increase by a factor 4 to 5. And this is due that if you do some back of an envelope calculation, to the fact that if you give part of your gravitational energy to your turbulent energy, as the turbulent energy scales with the sigma squared, you're not able to bring a lot you cannot increase a lot your velocity dispersion by a release of gravitational energy. So you have kind of a saturation of turbulence and a weak augmentation of compression, a weak star formation increase, because at the end of the day, what your turbulence does is to bring gas to the high density end. So here you have, for instance, the evolution of the gas PDF for gas poor mergers and gas rich merger. During your collision, you're able to bring a lot of gas to the high density end for the gas poor case. It's not the case for the gas rich case, because your PDF is already very wide. The width of the PDF is a function of the increasing function of the Mach number here. So if your Mach number is already very high, you cannot increase it by a lot. You're not going to increase a lot the width of your PDF. You will not bring a lot of gas to the high density end, and you will not increase a lot your star formation. And that's exactly what we see in the simulations. In the gas poor collision, you can increase your star formation rate by a factor 40. It's not the case for gas-rich galaxies, where it's an increase of a factor 4, which is barely what you need to be considered as a starburst. So for the same orbit, for the same galaxy models, it's very hard to trigger a starburst because of the already very high turbulence of young galaxies. Right, so what are we missing else in what we model for redshift 2 galaxies? So as I said in the introduction, the UV rest frame structure of those galaxies is very clumpy. So as a comparison here below those two very clumpy galaxies, you have an example of M81, which is seen here by Galax in the UV, and what we should see if we put M81 to redshift 2. So you see that it's not clumpy at all, right? You see spiral arms, which is not the case for redshift 1 galaxy. So it's not an effect of the K correction, right? And there is nothing to see with what is happening for illustrious CNG, neither Fire or Nihao, but there are some interesting things that is happening with Vela simulations, the extreme horizon simulation that shows some clumpy disks, which is interesting, is that those two simulations are done with IMR and not SPH or moving mesh like the other ones, but that's something we can discuss later on. And this question of giant clumps is actually at the heart of a very huge debate, which is triggered by observational data first, meaning that the clumpy UV morphology sometimes do not show in deep submillimeter data. So on the left, you have data from the dust continuum by Rob Ivison of the Eyelash galaxy, which was thought to be clumpy 10 years ago with data from the SMA by Swinbank et al. But with very deep ALMA observations, is super smooth. And on the right, you have the counterpart in the dense gas CO transition, 0.5 to 4 of the Skywalker galaxy, which, I mean, you have a lot of clumps in UV, but all the CO come from the center. But that was very strange because we see those clumps in the UV. So what does it mean? Is it because the gas consumption is very rapid, or what's happening? So one of the clues may be that when you have a too high resolution, either because you're using ALMA or you're observing a lensed galaxy, like the one on the cosmic snake on the right, you might be actually over-resolving those giant clumps, which are composed of subclumps, substructures. And that's what we saw with the studies of Baptiste Faure, who defended this thesis 2 weeks ago. So here you have a clumpy galaxy on the upper left. What we see when convolved with HST PSF, without taking any noise or any, I mean, that's pure translation into with PSF, and then convolved through on the right with a lensing model from Yuan Richard. So what you see, I'm trying to play the movie again, is that this lens is actually, I mean, you see many more clumps when you're using a lens because you're actually stretching your observations, and you don't resolve the big clumps, which are actually unresolved accumulation of smaller structures. And this corresponds to what is observed with lensed galaxies, for instance, here the cosmic snake, where you don't see the same number of substructures in the different counter images. So here for the snake, you have 4 different images: the snake north here in blue, the snake south in the south, then the central north and south in the middle, and a 4th image, which was on the other side of the galaxy cluster, image C. And it's, I mean, the fact that you don't see the same and you don't have the same mass spectrum of structures is actually explained by the fact that you're over-resolving the structures, right? It also works when you do ALMA mock observations. It's always done without any noise. It's just like infinite resolution. On the top left, what you see is what happens when you take a clumpy galaxy convolved with HST PSF. So here's the small red rectangle here is what you would get from a clump finder on this image. Is over-resolved with a lens, then you not get full clump, but only 2 small clumps. And then if you go to the high-resolution image, you still have the same red contour, but what you would see with ALMA is only the blue circles here, right? So here there was a test on the bottom with different resolution for ALMA, so in arc seconds. And what we see compared to other observations, or non-detections of clumps with ALMA data, is that if you take very high resolution, most of your clumps fall below the detection limit from, for instance, this paper by Rougeau-Packard. So obviously, I mean, we are only in the same order of magnitude. This galaxy model was used because it's super clumpy. Maybe the galaxies that were observed are not so clumpy at all. But we are in the same order of magnitude, right? Each clump at that resolution only contains 4 to 5% of the total flux of the galaxy in that wavelength, right? So that might explain why we are missing those clumps. We are actually filtering out the scales for which we would resolve them, right? This problem is not only observational; it's only seen in observation. So here you have the full panel, fire simulations on the top left. In this simulation, clumps are only living 20 mega years. On the top right, illustrious NG, there are no clumps at all. The Nihao simulations, this paper from Buck et al. Said that, they see only clumps in the light, so they infer that it might be due to only patchy dust distributions. But in some races simulations, but also simulations using ART or the Villa simulations, we see some clumps. And but I will not extend too much on this subject. So what is the main difference between the simulations who see clumps and those who don't see clumps? And the difference is the gas fraction. So in observations on the top, you see that the gas fraction is actually a very good proxy for the redshift of observation of star-forming galaxies. So it's an increasing. So here here you see the gas fraction, which is a mass of gas divided by the total baryonic mass. Here it's only in molecular hydrogen because it's harder to observe. It's not possible to observe atomic phases at high redshift yet. And you see that for observation, I mean, it's a monotonically increasing function. And at redshift 2, star-forming galaxies usually have half of their baryonic mass into the gas phase, which is not the case in simulations. Here, for instance, in the fire simulation, the gas fraction is around 30%. And this is actually including the gas in the halo, if you look at the paper, whereas on the top, it's only the molecular gas, right? So on top, we are underestimating the gas content, and in the simulations, we are overestimating this 30%, right? It's also the same in the paper on Illustris, the Illustris paper, when the gas fraction inside 2 times the effective radius at redshift 2 is more around 15%. It's not 50 at all, right? So modeled galaxies in those simulations are gas depleted at redshift 2, and this makes a lot of difference when we think about disk stability, right? So this is just a reminder of the Tumray stability analysis. Where you see that, I mean, that's only an analysis where the Tumray is the Tumray parameter, which is the competition between shear, turbulent support, and gravity. If you add a component, a gaseous component, you obtain something for which you see that if you increase the gas fraction, you will reduce the Q, and you will lead to more violent instabilities, and not have spiral arms, but a clumpy disk. That's exactly what we see in simulations that were published this year with Frédéric Bourneau. So if you take the same galaxy model with different gas fraction, you see that if you have a gas fraction from cosmological simulation, you only have spiral arms, and you have clumps when you go to a realistic gas fraction. So of course we have problems with the feedback, because that's a problem that we will all have for the next 50 years. It's very hard to calibrate the feedback. So our way to calibrate it is to use a galaxy-wide mass loading factor around 1, which corresponds to observations. And we see that for this feedback, our clumps are actually bounded only for the gas-rich case. So here you have what we have for the gas fraction that corresponds to the fire simulation. So those clumps have a virial parameter which is above 1. They are unbound, and they are bound for the gas-rich case. How much time do I have left? I think I was a bit too slow.
Sorry,
okay. I will just move.
You have 1 minute.
Okay, that's what I thought. I was a bit too long. So just to summarize, the gas fraction explains the irregular morphologies of galaxies, and in cosmological simulations, galaxies convert their gas too efficiently into stars, and that brings us back to the main question: how do you regulate star formation without ejecting all your gas? So we've seen before that one way is to bring some energy, like turbulent energy, for instance, in the study from Noé, that will be able to reduce the star formation efficiency in this environment. But this is only an idealized simulation. What we want to do is to bridge the scales between galaxy and cloud scales. And that's a study that I'm currently doing using a PRACE allocation that I got this year. Simulation just over. I don't have still the only preliminary results that we present probably next year at the next REM meeting. So those simulations have nested zooms that bring the resolution down to level 20 when I'm only using hydra and gravity, and to level 18 with radiative transfer and mechanical feedback. And that's where I leave you here. So see you next year to present the results on the nested zooms inside a gas-rich galaxy.
Thanks a lot, Jeremy. Any questions? Johan, I will keep yours to the side for the moment, because I would prefer the students or young postdocs to ask first. Francesca? Francesca, you're muted in case you're talking.
Sorry, that's my bad. You can unmute me.
Yes, now I can unmute. Yes. Thanks for the nice talk, Jeremy. I was wondering, so you mentioned quite in the beginning of the talk about how, for example, in the TNG simulations, the galaxies are very smooth and have disks at high redshift. compared to the observations. I was wondering what you think, and if you could comment on the results for example, from Rizzo last year, who was showing that at high redshift, they already have these very settled disks at redshift like 3 or 4 using lensing. Does that then tell us that galaxies should be clumpy or should be in these more disk-like smooth morphologies?
Can you just, I missed the name of the study.
There's been a couple of studies, but the one I remember quite clearly is the paper by Rizzo. It was like a Nature paper using lensing.
So maybe I missed it. So it's okay. So you're referring to this kind of observations, right? So when you're using...
and just from the beginning, you were talking about how we expect from observations these galaxies to be very clumpy, right, at high redshifts. But I'm wondering a bit. I don't know much about the high redshift galaxies, so I'm wondering what your take is on some of the studies that are finding these very nicely rotating settled disks at redshifts 3, 4, for example.
So yeah, so what you have to see is that even on the Skywalker galaxy, so this one on the right, what we see as clumps is a UV light. So you see where only the new stars are forming. But if you look at the gas rotation curves, I mean, all the studies and the SINS survey and the CHEMO 3D surveys show that those are rotating disks. Which, yeah, because when they were discovered, people thought, yeah, those are mergers. Yeah, don't worry about them. They are only mergers. But when you look at the gas kinematics, you see that they are rotating disks. And there are, I mean, those things are not decoupled from, I mean, kinematically decoupled from the disks. So yeah, so what we are this, I mean, yeah. So the main picture is that the morphology is very clumpy. I mean, it's the star formation rate is clumpy. But if you look at the old stars, and they will be much smoother. And about the dust continuum and the gas distribution, this is a very hot subject. I mean, there are a lot of studies, for example, from Hodge, Jacqueline Hodge, who showed a lot of, I mean, that when you observe gas, dust, and stars, I mean, they don't overlap at all for high redshift galaxies. So what would happen is, I mean, there are some ideas. So the fact that you might have some dust destructions in some places, you might be very quick at depleting your gas in those clumps, for instance. Maybe the gas, the CO can be destroyed by cosmic rays and you can't see it where you form a lot of stars. I mean, there are a lot of theories and...
Yeah, and maybe just a more technical question about the point you were making about how the gas fraction is very important. So do you think also the equation of state can play a role in why, for example, the TNG simulations have a much smoother distribution rather than the gas fraction itself? Do you not think that the star formation recipe itself also plays a role in the feedback prescription?
I think it's, I mean, when we look at the papers on the outflow rates, so there was a paper by Dylan Nelson. On this, we see that their mass loading factors are much more than 1. It's more around 5 to 10. So it's up, I mean, almost an order of magnitude too high. So my take on this is that, I mean, because all their galaxies are on the main sequence, so they form they have the right SFR for the stellar mass. So what I suppose that their gas arrives and is consumed or expelled very fast. So you don't keep a lot of gas in your disk. You form stars at a rate which is correct for the stellar mass, but you eject your gas too fast. So you don't have these instabilities that develop. So what we have to find is how to, maybe, I don't know if it's a matter of resolution or a matter of missing physics, but how to find a way to keep your gas in the disk without ejecting it and without having him forming stars. So that's what's happening with the turbulence forcing with Noé, for instance. It's a way to prevent the gas from fragmenting and forming stars. You keep it in the disk, but it's not forming stars and it's dense enough not to be ejected. So that's, for instance, could be a solution to this problem.
Johan, if it's brief. Unless it was an announcement.
No, there will be an announcement after. But no, the question is brief, but probably the answer will be long. So the question is about the observations. You show that the molecular content is large at high redshift, can reach 50% or so. Those observations, if I understood correctly, are based on CO2H2 conversion factors in general, which has been challenged in the past in their ability to actually track the CO2H2 conversion at high redshift, because it's based at low redshift, right? So, I mean, to what extent should we take those results at high redshift for granted?
So, yeah. And the CO2H2 factor is a very huge problem, and it's not easily tackled because you need a reference. So I'm not an expert on that, but I remember there were some studies using the large velocity gradient methods to try to model the self-absorption of gas of CO lines inside disks that show that even if you have even for gas-rich galaxies, thanks to the high turbulence, you would not change too much this alpha factor in high redshift galaxies. I mean, high redshift in redshift 2 galaxies. But it's only preliminary work, right? I mean, there might be a lot of effects, including cosmic rays, for instance, and that is an avenue of research that must be. Yeah, I don't have an answer.
This will alleviate a lot of the tensions of the simulation of the observations, right? If you reduce molecular content estimated from observation, it's much easier for simulations, right?
It could, but one big problem for simulations as well is the morphologies.
Sure, but that's probably another issue.
Yeah, but I mean, to my mind, they're related. But I mean, having the right gas fraction could solve both at the same time. So if we are wrong about the gas fraction, we should be wrong somewhere on the clumpy and the clumpy morphologies as well.
Okay.
I don't know, but maybe we can discuss that later.
So, Kuro, do you mind asking your question over Slack? If you don't, we don't want to eat too much into the coffee break. Sorry about that. Given that we have to take the conference picture.
Yeah, so